Good morning, class. Thank you for coming back. This is Monday. I'm physically in France. This is a pre-recorded lecture that I prepared before the trip. Today, I'm going to talk about this lecture on function of random variables. It is a very difficult topic that many of students, they struggle to understand. So I want to start by giving you an example. This is the electrical engineering 101 equation. Voltage equals to current times resistor, and power equals to current squared times the resistance. Suppose I have the measurement of the current, which is a random variable. I have this random variable. I want to ask what is the distribution of the power, meaning that I tell you the PDF of I ask you what is the PDF of P. So in this case, I cannot just say, hey, my current follows a, let's say, a Gaussian distribution, and therefore the power will be the Gaussian distribution square. That doesn't work. Remember, we never do anything to the PDF. We never square or shift this PDF. We always go through a formal process of deriving the PDF. So it is all this topic about. So what should we do here? Let me start by summarizing the problem. You know a random variable x, meaning that you know the PDF of x. You also know the CDF of x. Okay, so these two are known. If I give you one, you should be able to derive the other, or if I give you the other, you should be able to derive the first one. So I tell you this. And then I also provide you a function g. And this g will be applied to the random variable x to give you this random variable y. So there is a transformation that's happening. Well, this g can be a square, like the current and also the power example, or this g can be a sine of x, or if you want, a g of x can be e to the power x. So it can be any transformation that you can think of. Then I ask, can you find me the PDF of this new random variable y, including the CDF and also the PDF? Instead of telling you the exact derivation, the principle, I want to start by telling you 4 examples. I'm going to talk about at least one example and see how much time I have, maybe go through another example. But Kent will be here to give you additional examples on this list. So the way that I'm going to do it is that I will give you the PDF and CDF of random variable. I'm going to give you a transformation G, and then I will ask you to find the PDF and CDF of the new random variable, and express your answer in terms of the original PDF and the CDF. So without further ado, let's look at this problem, the first problem, where you know the PDF and CDF of a random variable x, and the transformation is a linear transformation, and I want to find the PDF and CDF. So I come back to this principal diagram later on. So let's just go straight into this problem. Okay, so let x be a random variable with a PDF and CDF, which I am not specifying yet. Now, it could be a uniform, it could be a Gaussian, it could be something. I let y equals to 2x plus 3. And I want to find the PDF of y and the CDF of y. So how should we do? Now, let's start by looking at the CDF of y, because this is one of the 2 quantities we want to derive. And we also know that if I know the CDF of y, I can take the derivative to get the PDF of y. So let's start with the CDF. So the CDF of y is the probability that y is less than small y. That is just the definition of a CDF. Now, what is this y? The random variable y, according to the problem setting, it is 2x plus 3. So you have 2x plus 3 less than small y. Now, at this point, you may be confused. There are two variables. One is x, one is y. Do not get confused. This is the random variable, and here is the state. The state is always a constant with respect to your random variable. So you can, if you don't like this y, you can put an apple, you can put an orange. It's just a number. So as we are evaluating this probability, we know that this is the probability of 2x plus 3 less than or equals to y. So let us express this probability in terms of x. So I want to say x is less than or equals to something. And this something would be y minus 3 divided by 2. I just move around the terms. 2x plus 3 will become y minus 3 divided by 2. Just move around the terms. Then you can see that here I am evaluating the probability of the random variable x at the point of y minus 3 divided by 2. This is y minus 3 divided by 2. So this is just a number. It's the state that you are evaluating. Okay, so this is a probability. And what is this probability? This is just the integration, right, of this random variable from minus infinity up to a point. The point is y minus 3 divided by 2 using your fx dx. And what is this? This is nothing but just the CDF of the random variable x evaluated at y minus 3 divided by 2. And therefore, I have found the CDF of y, which is the CDF of x evaluated at y minus 3 divided by 2. So life is good. And let's see, how do we calculate the PDF? The PDF is the derivative with respect to your y. So in this case, it will be d dy of your fx of y minus 3 divided by 2. Right? I'm just copy and paste this CDF here. Now, what is this integration? This is d dy, right? So that is a fx here. This thing is just the integration from minus infinity to y minus 3 divided by 2 of your fx dx. Okay, so this is a derivative of an integral where the variable y is sitting in the upper limit. So how do we calculate this derivative? This derivative, if you recall, there is a very useful formula. It's the fundamental theorem of calculus. It says that if you are integrating something from a to y of ft dt, this is going to be f of t. Okay, so this is the fundamental theorem of calculus that we have reviewed in the first chapter of our book. So let's go back to here. This one is the derivative of this integral with respect to y, but there is a mismatch between this y and y minus 3 divided by 2. So what can we do here? Well, let's do this, d of y minus 3 divided by 2, so that we can match the upper limit and also the derivative. Okay, so we can match that. But in order to match that, we also need to do this transformation. So you are going to take this d of this term and by dy. So this is like a substitution. You need to take care of that additional thing that you are looking at. So what is this? This has the exact same form as what we see in this fundamental theorem calculus. And this is going to give you f evaluated at, now not y, but y minus 3 divided by 2, because your upper limit is y minus 3 divided by 2. There is one additional term here, which is the derivative of y minus 3 divided by 2. And so that is going to be 1/2, because this d of y minus 3 divided by 2 dy is going to give you 1/2. Okay, so that is this term here. And so to conclude, in this problem, the PDF of this random variable y will be this. It's 1/2 of the PDF of x evaluated at y minus 3 divided by 2. So I hope this example gives you some ideas how do we do it. Now, if you have a Gaussian random variable, you can put down the Gaussian CDF. You have a uniform random variable, you can put down the uniform CDF and PDF there. So example number 2, I will leave it to Kent. And let me talk about example number 3. In this example, we are looking at a uniform random variable. X is between 0 and 2 pi. And suppose y equals to cosine of x. And I want to find the PDF and also the CDF of this random variable y. Now, in this example, it's unlike the previous example where we just use a generic PDF and CDF. Here, we want to know the specific, very, very specific PDF and CDF. So it is a uniform random variable. Now, what will be the PDF? The PDF of this x will be 1/2 pi, where x is between 0 and 2 pi. And it is 0 otherwise. So what would be the CDF? The CDF, of course, it has to be 0 and 1 if x is less than 0 and if x is bigger than 2 pi. So there are 3 cases. So x is between 0 and 2 pi. But for the thing that's inside, in the middle, we know that this is CDF. The CDF has to be the integration from minus infinity to x of your ft dt. T is a dummy variable. So in our case, it will be the integration from 0 to x, and then here it will be 1/2 pi dt. And so if you do this integration, it will give you x divided by 2 pi. So we have found the CDF of this uniform random variable. So fx equals to x divided by 2 pi. So that's the CDF. And then the PDF is given by this equation here. So we know the CDF and PDF of the original random variable x. And now let's look at the new random variable y, which is cosine of x. Okay, so how do we calculate that? Well, the CDF of the y, right? We always start with the CDF because we know that the PDF can be derived by taking the derivative of the CDF. The CDF of y is the probability that y is less than equals to small y. Okay, and now what is this y? This is just cosine of x less than or equals to small y. So now you have this cosine x is less than or equals to small y. So clearly what we want to do is to take the inversion, right? So take the cosine inverse and then put it onto the right-hand side. But before I do that, let me just draw a picture to see if there is anything hidden that I need to pay attention to. So this is my cosine of x. This is x, okay? So I want to do the inversion. In other words, I want to find the x such that it is less than or equals to y. So let me say that y is here. Y is this horizontal line. I want to find all the x that is less than or equals to y. So there's a range. The range would be from here all the way to there. So there's a range of x. And so not only that, I want to find not just taking the cosine inverse on y, I also need to take care of this range of numbers. And so that range of numbers will be the probability that your x is between two numbers, right? So the first number, it will be cosine inverse of y, which is if you start with y, then you go down, that will of course be the cosine inverse of y. The other one will actually be this side. It will be 2 pi minus cosine inverse of y. So you have this range of two ends. Then we can evaluate these two ends according to the CDF. The CDF applied to the upper limit minus the CDF applied to the lower limit. Then you can go to this expression. Okay, so that will be the difference between these two CDFs. Then what can I do? Well, then this thing is just your CDF. So you know the expression, which is 2 pi minus cosine inverse of y divided by 2 pi. Where does it come from? Because your CDF evaluated at x is just x divided by 2 pi. So just substitute this into this equation here. And this guy will be cosine inverse of y divided by 2 pi. Okay, so that would be this term. And so you take this difference, then you can get to 1 minus cosine inverse y divided by pi. The two will be absorbed. So that is my CDF. Your CDF is given by this ugly formula. This is the CDF of your random variable y. Now, how do I calculate the PDF? Well, we know the PDF is that if this is your CDF, then your PDF will be the derivative of your CDF. So you're going to take the derivative of this cosine inverse y. So how do we do that? So that is something that you need to go back to your calculus textbook, but let me remind you how do we do it. This is the formula. Cosine inverse of y, if you take the derivative with respect to y, you can get to this formula. And you may wonder why. Okay, so let's draw a triangle. There's a theta, there's a y, there's a 1. Okay, so that is your triangle. We ask, what is this cosine of theta? Cosine of theta is y. Okay, cosine of theta is y. So let's take the derivative with respect to your theta. Let's take the derivative with respect to your theta. So cosine theta, it will be dy d theta. And then what is the cosine theta? Cosine theta is minus sine theta. So that's going to give you dy d theta. Okay? So in this diagram, what is the theta? The theta, it will be y squared minus 1. This is y squared minus 1, correct? Okay? And that's going to give you this dy d theta. So how are we going to calculate this cosine inverse of y? Then let me see if I do it right. Okay, so so what is cosine inverse of y? Cosine of inverse of y is just theta, right? So if I want to take the derivative with respect to y, then I'm really taking the derivative with respect to of theta with respect to y. Okay, so this is going to give me. If I want to get this thing here, this is the same as 1 over dy and d theta. Okay, so if I have that, oh, sorry, I should have a square root here. Then if I do this, then it will become 1 over y squared minus 1. There's also a minus here. Okay. Wait a minute, I think I have something wrong. Am I right? Did I make some mistake here? Why is it 1 minus y squared? Oh, I think, okay, I think this is, I think I make a mistake here. This should be 1. That should be y. Okay. Right? So that should be y, this should be 1. And so because cosine of theta is y, right? And so my bad. And so that is sine of theta. Because the sine of theta, it will just be this height, right? So this height is 1 minus y squared root. And so this thing here is not y squared minus 1, but it's 1 minus y squared root. And so I go back to here, that will give me minus 1 of 1 minus y squared. Okay, so that is the trick. So once we have found the derivative of this cosine inverse of y, we can go back to the previous slide here. What do we want? Well, we want to find this PDF of this random variable, and therefore we need to calculate this derivative with respect to y. Cosine inverse of y, we have already found the formula, so we can plug it in. Then we can get to this result of 1 over pi root of 1 minus y squared. Okay, so sorry for the little confusion here, but I think right now we are clear about what we're doing. So let me tell you, go back into this slide. This is page number 5, about the principle. Okay, so as you can see in these two examples, what we have been doing is that we always start with the CDF. We start with the CDF, and there is a mapping. There's a mapping that's given by this G, and this mapping will map the CDF to the new CDF, where you can see that in the original the CDF, all these random samples, they're uniformly random. They're uniformly spaced because in this case, I'm looking at this a uniform CDF here. Now you can of course replace this uniform CDF by another CDF. You start with this, and then you map it through this G function, and then you sort of squeeze and you stretch the location of these random variables. And then you go to this CDF here, then you take the derivative and you get the PDF. So there is a mapping from the CDF to the new CDF to the PDF. So that is the general principle that how you can solve these problems. So Ken will be here in a moment to talk about 2 additional examples, example number 2 and example number 4. As you're working on your homework problems, you will be able to see a lot more of these examples. In the textbook, you will also see a lot of these examples to work on problems like that. So take a minute to think about these problems, and then please welcome Ken to talk about additional problems. And I will see you in the next recording. Thank you very much.
Okay. Example 2. So we have a square of a uniform random variable. So suppose x is uniform in this interval AB, and you have y, which is x squared. Then you want to compute the CDF and the PDF of y, respectively. So you end up with these final results here. Maybe we should derive it as a group to see how we got there. So we've got this, the probability that x squared is less than x. Right here we'll do f y is equal to probability y less than y, right? Which is equal to the probability that x squared is less than y, which is equal to the probability, now you've got a parabola, right? Okay, so this is x squared. So now you know that if you have a particular y value, You could have had this one or this one. Okay. So now you need to have the probability that if it's less than y, it's going to be below that interval. So you've got, let's think about this. Do it correctly the first time. Cool. Okay, you know that that's going to be equal to this. Right? Because you've got this interval, you've got this interval. You just want this region. This is everything to the left, and this is everything below. And so when you take the difference, well, I guess we should have maybe done it like this. And you take the difference between them, you end up with just the region you want. Okay. Cool. So you get this thing. You know that this is just going to be the uniform, so we can copy this, and you end up with the answer. Cool. Oh. Okay. So that's this one. We're happy. We need to get these, but you can figure that out because you know that if x is from, so we know that x, or little x here, square root of y, has to be between a, square root of y, b, it's a squared, y, b squared. Rock on. Now we want to take the derivative with respect to y. And if you do all of the work, you end up with this form here. I don't know if it's worth doing all of the algebra. I guess we could, but it's just some arithmetic. But does that make sense for the uniform case? What's interesting? Yeah. I think I see what you're saying. You're saying this should be probability 0. That's a good point. I see. So you've got this a greater than 0, and you've got this thing which is less than 0 since the square root is going to be a positive value. And x will always be less than a positive value. Yeah, let's think. Yeah, I do see what you're saying. Yeah, I'll have to think about it and get back to you. That's a good question. Yeah. Okay. We'll think about example 2. Okay. Are there any other questions on this? Okay. So now I'll do example 4. So we let x be a random variable with this PDF. And so you've got something that looks kind of gross, because you have e to the x, and then e to the also e to the x. And now you're letting this be another e to the x. So just to make it explicit, you've got, so now you're trying to find fyy. So you need to get you've got this. And you know that exponential of x looks something like this, right? So this is e to the x. Okay, cool. And so you know, I guess we could have done this on separate lines, but then you know that this is going to be the PMF of, so this is just the CDF of x. You can plug in this down here, and then this integral is the definition of the PDF of x. So in this example, we're not going to simplify it because it's, oh, I guess we could simplify it on the next page. So we'll simplify it on the next page. But it obviously looks kind of gross. Does this set up fine? Okay. So then on the next page, we're going to try to simplify the sum. Oh, because we can. So this fy is really gross, but now we're going to take a derivative, right? And what's nice is that we're going to take a derivative with respect to y. The only y here is this limit. So we can probably apply some rule to make our life easier. So I think we can just do the fundamental theorem of calculus, yeah? So we've got, okay. So we've got this. We know from the fundamental theorem of calculus that this is going to be fy at log y, or fx at log y minus fx at negative infinity. Okay, which is going to be equal to the right, and then we can use our rule to get that this is the, we have to take the derivative first, so we get a e log y e to the negative a. Whew. And then we have to get the other term, so this is the first term, and then we have to do chain rule, so we have to multiply by 1 over y. Okay, and then we can simplify this down. Ends up being a times y times e to the negative a y times 1 over y, which is equal to u, but we did it. Okay. Is that okay? Escaped the really gross thing. And it turned out it was all fine. It was easy to do. Okay. Cool. So then I think he covered everything else, right? He covered this slide? Okay. So then are there any general questions? Because we have time left, we'll just go through some practice problems in the textbook.